we have seen 3 times that GNNs inherit the stability properties of the filter classes that make up their layers. This is because we can write a generic inheritance proof. Let's repeat the proof, which we already did for the particular case of dilations, for the more general case of relative perturbations and integral Lipschitz filters. But this time we pay attention to the fact that steps apply to any stability claim that we make on any filter class. And we take this chance to explain how GNNs inherit their stability properties from graph filters. The theorem we want to prove assumes that the layers of a given GNN are made up of integral Lipschitz filters. If this is the case, we can prove stability to relative deformations, in which the perturbed shift operator S hat can be written as the sum of S with the symmetric multiplicative error term E times S plus S times E, modulo permutation, as usual. To write down a proof, we utilize these slides, which are the same ones we use for the dilation proof. As we did there, let XL be the output of the lth layer of the GNN defined on the shift operator S. And X hat L denote the lth layered output of the GNN defined on the perturbed shift operator S hat. The two GNNs start with the same input, but as the shift operators are different, layer outputs are different. This input signal X has unit norm because we are interested in computing the operator norm difference between the GNNs. With these definitions, we compare the output of layer L of the GNN defined over S hat with the output of layer L of the GNN defined over S. This difference can be rewritten in terms of the outputs of the previous layers, X hat L minus 1 and XL minus 1. It suffices for us to recall that the layer is a graph perceptron composing a pointwise nonlinearity sigma with a graph convolution. We now invoke our assumption that the nonlinearities in the GNN are normalized Lipschitz to bound the difference on the output of the nonlinearity function in terms of its inputs. But the inputs to the nonlinearity are the graph convolutions computed at layer L. Thus, we can bound the difference between the outputs of the two layers L by the difference of the graph convolutions themselves. This is, we recall, the critical step of the proof. It eliminates the nonlinearity from the analysis. The rest is simple algebra. We start the algebra with the bound we have just obtained. In the right-hand side, we add and subtract the result of applying the graph convolution defined by S hat on the signal that is produced by the GNN that runs on graph S at the output of layer L-1. The cross product across the different GNNs is relevant here. As the distance modulo permutation is a proper norm, we can proceed to use the triangle inequality to separate the norm into a term depending on the signal XL-1 and another term depending on the difference between XL-1 and X hat L-1. The norm is also submultiplicative, allowing us to further break down each of these two terms into the product between the norm of a filter and the norm of a signal. We now recall that we have assumed the filters to be normalized, from where we can say that the norm of the filter HL of S hat equals to 1. And since the nonlinearities are also normalized, we can further say that the norm of the graph signal XL-1 is also bounded by 1. This leaves us with a term depending on the difference between the filters of layer L, and a term depending on the difference between the signals received from the previous layer, the signals X hat and X at layer L-1. Up until now, none of the analysis depends on the filter choice. But in this step, we invoke the stability property of the filter class. Since we are considering relative perturbations and integral Lipschitz filters, we utilize the theorem proving stability of integral Lipschitz filters to relative perturbations. In such theorem, the bound is of the form 2 times c times 1 plus delta square root of n times epsilon. This is therefore the bound that we will use. But if the stability claim were different, we just need to modify this step. The rest of the proof remains unchanged. If we wanted to prove the GNN theorem for additive perturbations, we would need to change the hypothesis for us to be able to invoke the stability of Lipschitz filters to additive perturbations and utilize the appropriate constant, which would be the same without the 2 factor. But in this particular proof, we are dealing with relative perturbations and integral Lipschitz filters. We therefore substitute the bound 2 times c times 1 plus delta square root of n times epsilon. With this, we obtain a recursion that we can apply backwards from layer L up to layer 1. The bound has the same form for all layers, from which we get the L factor in the stability bound of the GNN, as we wanted to prove. The fact that stability is inherited from graph filters implies that, mutatis mutandis, the same observations we made for graph filters also hold here. We claim stability, which is stronger than continuity. The stability bounds are universal. They hold for GNNs run on all graphs with a given number of nodes. And set bounds depend on C, the Lipschitz constant of the filter, and on L, the number of layers of the GNN. These are parameters we control. But the bound also depends on the eigenvector misalignment constant, which we don't control. It's a property of the perturbation. As was the case of graph filters, we proved a theorem for additive perturbations and another theorem for relative perturbations. The stability claim for additive perturbations is that GNNs with Lipschitz layers are stable to additive perturbations of the shift. This is good news, because we know that Lipschitz filters offer a genuine stability versus discriminability trade-off. Alas, the result is a little bit of a mirage. It is more natural to measure graph perturbations in relative terms than it is to measure them in absolute terms. Meaningful stability claims are with respect to relative perturbations, and stability to relative perturbations requires that we use integral Lipschitz filters. This is unmitigated bad news. We have stressed repeatedly that integral Lipschitz filters must be flat at high frequencies. This is a serious limitation. It precludes the discrimination of high-frequency features. It is impossible for integral Lipschitz filters to separate signals with high-frequency features. And since we necessitate of integral Lipschitz filters for stability, it follows that it is impossible for graph filters to discriminate high-frequency features and be stable to deformations simultaneously. You just can't do it. Now, on the flip side, integral Lipschitz filters can be very sharp at low frequencies. They have high discriminability when the frequency argument is close to 0. And this means that for features that are located at low frequencies, integral Lipschitz filters can be very discriminative. And since integral Lipschitz filters lead to stability, they can be, at the same time, very stable to deformations as well. We do not need a large constant C for an integral Lipschitz filter to be discriminative around frequency 0. Stability and discriminability are compatible. The low discriminability at high frequencies and the high discriminability at low frequencies add properties of filters that layers of the GNN inherit. But while the GNN as a whole inherits the stability of the filters, it doesn't have to inherit their discriminability limitations. In fact, avoiding this fight is the role of the nonlinearity. The nonlinearity is a low-pass operation that demodulates high-frequency components into low frequencies, where they can be discriminated sharply with a stable filter at the next layer. Thus, GNNs can be both stable and discriminative. They can be stable if they use integral Lipschitz filters, and they can be discriminative by demodulating high-frequency components into low-frequency components. They do that with low-pass point-wise nonlinearities in order to enable their stable discrimination in deeper layers. This is a trade-off that linear filters cannot achieve. They are either discriminative or stable, but they can't be both. That GNNs can be both stable and discriminative explains their better performance relative to linear graph